It has been some time since we've gotten together as a class. I wish everyone well. Sorry about uh, the times that we haven't gotten together, but we'll make up for it as we move forward to the class. The last chapter that we talked about was arch and garch models. Now we're moving into another realm of econometrics. This starts with qualitative choice models. The best way to do this, I suppose, is to follow along the PowerPoint slides, and I will try to guide you through each of the slides. So if you need to, I want you to turn to Chapter 13, Qualitative Choice Models, and we'll discuss these. Actually, the next couple of lectures deal with the whole concept of limited dependent variables. And in the case of limited dependent variables, you have three types essentially. Number one, where the dependent variable corresponds to discrete choices. And in this chapter, we're going to be talking about the binary choice models, that is, two choices. But it is possible to have more than two, and that would lead you to a polycotomous choice or multiple choice model. The other type of model that we'll talk about in the next chapter, chapter 14, is the censored response model. This is where the dependent variable is discontinuous, and we'll discuss that in detail. The third type is an integer valued dependent variable, and an integer valued dependent variable, uh, the dependent variable actually corresponds to counts. For example, the number of trips one may take to a national park, or the number of trips you may take to restaurants. And really good references for these three choice type of limited dependent variable models are Green and Madala, as indicated on slide 2 of the PowerPoint. Um, in the case of integer valued or count data models, we will not be discussing those because we have limited amounts of time. However, if the need arises, I can always provide additional information. In the case of models where the dependent variables correspond to choices, we'll be covering the probit and the logit models. In the case of censored response models, we'll be talking about the Tobin model and the Heckman sample selection procedure. Now on page 4 of the, or slide 4 of the PowerPoint, we begin our discussion with binary choice models. So the dependent variable represents the occurrence of an event or a choice between two alternatives. And the example on slide 4, we're talking about the dependent variable corresponding to employment status. That is, we have a cross-sectional data set, and frankly, most of the choice models that we will be dealing with, the underlying data corresponding to these are cross-sectional data. So in this case, the cross-section is a set of individuals, and in the sample, the individuals either are employed or not. What we want to find out is whether or not differences in age, educational attainment, race, marital status, and perhaps other observable characteristics, for example, region or ethnicity, whether or not these factors affect whether or not an individual is employed or not. Ultimately, the dependent variable, the predicted value, will be some sort of uh, value that corresponds to the probability of being employed or not. And in the case of dichotomous choices, or binary choices, actually, there's three types of models. We'll first discuss the linear probability model, followed by the logit model, or the probit model, and then followed by the logit model. Now, in general, There have been a number uh, of instances where binary choice models were done. For example, on slide 5, participating or not participating in a government food assistance program. I did some work earlier dealing with the supplemental uh, nutritional assistance program. Eligible households uh, chose to either participate or not to participate. We actually wanted to determine the profile of those households who were participating. Buying or not buying a food or beverage product, which is something that we regularly do at the uh, Agribusiness Food and Consumer Economics Research Center. For example, a profile of those buying organic milk or those who may buy plant-based milk alternatives instead of conventional milk. So it's choice to buy or not to buy. Voting yes or no, although there could be other choices when it comes to voting. For example, not voting at all, or um, the other example, done some work for government dealing with the reporting or failing to report income, and we just talked about the employed or unemployed example. But the objective is to construct a profile of individuals or households who make one choice or the alternative. Two choices. Keep that in mind. So what is common among these? Well, the use of cross-sectional data, seeking probabilities conditional on a set of explanatory variables, and determining how changes in the explanatory variables affect the probabilities, marginal effects. So we're still after forecasts, but these will be probabilities. We're still after marginal effects, but the only difference is the dependent variable takes on a discrete choice. And typically, in the case of binary choices, the dependent variable will be a 0 or a 1, actually a dummy variable. So in the case of the linear probability model, the discrete nature of the dependent variable, or the dependent variable being a dummy variable, largely is ignored. It just, the analyst would just run the model, and this is evident on slide 6. X corresponds to the set of explanatory variables, and OLS still yields consistent and unbiased estimates of the parameters. The deficiencies are, though, are three. Number one, there could be heteroscedasticity of the disturbance terms. Number two, the distribution of the disturbance terms are not normal. But the most important deficiency is that it allows the predicted values to fall outside the interval of 0 or 1. And remember, our objective here is to get as a predicted value a probability. And of course, probabilities can only be in the interval from 0 to 1. Now, how do we guarantee that? Well, monotonic transformations. So we want to move away from the use of linear probability models, despite the fact that OLS yields consistent and unbiased estimates. So let's talk a little bit on slide 7 about the mechanics of these monotonic transformations. Now what we're going to do, we still have the same set of explanatory variables x, and we still need to estimate the parameter vector beta, but we're going to consider that linear combination and let that be equal to an index called z. So z is the linear combination of the parameter estimates together with the explanatory variables. And let's suppose that z star is a random variable and has a probability density function. Now remember, the dependent variable can only take on two values, 1 or 0. 1 if zi is greater than or equal to zi star, and 0 if zi is less than zi star. So if we consider the probability that y equals 1 given z, or given the set of explanatory variables and the parameter estimates, what we find is that the probability that y is equal to 1 is really the cumulative distribution function. And the alternative, y equals 0, is 1 minus that. So in the case of probabilities, we satisfy the fact, guaranteed, because the probabilities are associated with the cumulative distribution function. Those probabilities are guaranteed again to be between 0 and 1, and not only that, the probability that y equals 1 plus the probability that y equals 0 adds up to 1. Guaranteed. Very few things we can guarantee, but that's what we're seeing. Now, the question is, what is the appropriate cumulative distribution function? And we're going to consider two types, as I said earlier. The first is the probit model. And on slide 8, if you'll see the probit model, the probit model corresponds to the cumulative standard normal distribution function. That involves an integral. But remember, don't forget what z is. Z involves the data, the x's, as well as the unknown parameters. So once we get the estimates of the parameters, we can then get z. Once we have z, then we get the probability that y equals 1, but also we get the probability that y equals 0. Now the question is, how do you get the marginal effects? Now what the marginal effects are in the case of binary choice models is really the change in the probability due to a change in any one of the explanatory variables. Now these explanatory variables can either be discrete or non-discrete, but if you'll notice, the marginal effects are not equal to the parameter estimates. That's a common error in dealing with binary choice models. One needs to multiply the parameter estimates by the underlying probability density function, little f of zi, if you'll see that on slide 8. And what's also given is the probability density function for the standard normal. So once again, once the parameter estimates are obtained, we get an estimate of z for each observation, that is a subscript I, and we'll get an underlying probability density function. So the marginal effects involve the product of the parameter estimates and the probability density function, but since the probability density function varies for each observation, so will the marginal effects. So what we need to do is take an average, if you will, over all marginal effects, or alternatively pick the explanatory variables and set them at the sample means, get one z, get one probability density function evaluated at the sample means, and then the underlying product of that standard normal probability density function times the parameter estimates will give the appropriate marginal effects. In the case of the logit model, the logit model actually comes about from the early works of a researcher named Berkson. By the way, in the probit model, it grew out of the 1950s with the work of Finney. The Berkson model actually earlier than the probit model. But the logit model does not involve an integral. In fact, you'll see the cumulative distribution function on slide 9 here. That's equal to e to the zi divided by 1 plus e to the zi. So again, once we estimate the parameter estimates, we'll get the z. Once we get the z, we get the probability. Once we get the probability, we can get the marginal effects, and the underlying probability density function associated with the logit model is given as e to the zi divided by 1 plus e to the zi squared. Now, where does the term logit come from? Well, if you take a look at the underlying cumulative distribution function for the logit model. You can rewrite that as zi equals the log of pi, the probability, divided by 1 minus probability. The log of the ratio of the probability to its alternative, 1 minus pi, or the log of the odds ratio, as it's often termed, that is called the logit, and that's where the name logit actually comes from. So, given our initial setup here of either the probit model or the logit model, and by the way, these are the common underlying cumulative distribution functions, but there could be others as well, as many underlying cumulative distribution functions as you want. I've seen some studies deal with Weibull or other distributions, but in most cases, when it comes to binary choice models, probit and logit models are the most considered. So here's the question. How do we actually estimate the parameter beta? Now this sets off a chain reaction. Once we get the estimated parameter beta, then we can get z. Once we get z, then we get the underlying cumulative distribution function or the probability, and we also get the marginal effect. So it's important to figure out how do we actually get the estimator or the estimate of the parameter vector beta. What's going to happen here, since we are hypothesizing certain distributions, it's natural then to talk about maximum likelihood algorithms. Now, the maximum likelihood estimation procedure is also good in the sense that it assures the large sample properties of consistency and asymptotic normality of the parameter vectors, so that our conventional tests of significance that we used in conventional regression models, which don't have any limitations in the dependent variable, are still applicable. So what does the underlying likelihood function look like? And if you'll turn to slide 11, you'll see the actual write-up of the likelihood function, which really is the product of the individual probabilities of all observations, n in this case. And if we order the observations 1 through n1 such that they correspond to the first choice being made, that is the case where y equals 1, and the remaining n minus n1 observations corresponding to the situation where the dependent variable equals 0, and then consider the logarithm of that likelihood function, you'll see that you get a nice, convenient, closed form expression of the log likelihood function. And to obtain the estimator associated with the parameter vector, remember what pi is. Pi involves the underlying parameter vector. What we would do, or what the algorithm would do, is to differentiate the log likelihood function with respect to the underlying parameter and solve the system of normal equations. So it is a nonlinear procedure. Typically how this is done is with iterative methods, typically the quasi-Newton or Newton-Raphson method, as it's indicated on slide 12. And packages routinely will estimate these particular models. In the case of SAS, there's a proc-QLIM procedure, and at the end of the day, what's estimated is the underlying parameters. Now, we'll talk more about that, but let's first talk about goodness of fit measures for binary choice models. In general, the underlying data set associated with this analysis is cross-sectional data. So one normally would not expect a conventionally high goodness of fit statistic like an R-squared or adjusted R-squared. But remember, the dependent variable here in binary choice models is 0 or 1. So the only way we can really get a very high R-squared is if the predicted value, again a probability, is close to zero when the actual value of the dependent variable is zero, or in the case of when the dependent variable is 1, a predicted value that is very close to 1. Probably the most popular goodness of fit measure was instituted by McFadden in 1974, and given the fact that we're using likelihood procedures, we see the McFadden goodness of fit measure r squared sub m on slide 13, which is equal to 1 minus the log of the likelihood function involving the estimated parameters, and that natural log of L of 0 is when all the estimated parameters are equal to 0 except the intercept. Okay. The other measures here, one is called the Estrella measure, developed in 1998. It still involves the ratio of the log of the likelihood function L divided by the log of the likelihood function L0. Here's a picture of McFadden, the pioneer in that. By the way, Daniel McFadden won a Nobel Prize for his work in this area, as well as other works that he had done too. Other goodness of fit, here's an alternative version of the Estrella measure. But there's still others. One is called the Craig-Euler measure, or Craig-Euler measures, actually two of them. This is on slide 16. Another measure called the Aldrich-Nelson measure. Then we have the Vial-Zimmermann measure and the McKelvey-Zavonia measure. Except for the McKelvey-Zavonia measure, the common thread among all goodness of fits involves the log of the likelihood function. Which one do we use? Well, in most packages, what's actually calculated is the McFadden r squared, but SAS actually through ProcQLim will print them all. And often what analysts will do, of course, is to choose the highest measure here, and that would be their goodness of fit. But all of these are common measures of goodness of fit, again with the McFadden measure being the most common. Now, the other thing that we could do in terms of goodness of fit is to decide on how well our model actually classifies the outcome, either within sample or with a training sample or out of sample. But in order to do that, we have to have a mechanism that compares the predicted probability to a cutoff value. So that if the estimated probability is greater than the cutoff value, then we would say the first alternative is selected, and then determine whether or not the prediction of our first alternative being selected is actually the right one. Or if the estimated probability is less than the cutoff value, then we would predict the second alternative. So what we would like to see is a maximum proportion of correct classifications, but the fly in the ointment here is what is the appropriate cutoff. In most cases, analysts will use a cutoff of 0.5, but that may not be the appropriate cutoff. And what I've recommended, and you can see on slide 18, various sources here. Well, I've been involved with this cutoff. You'll see a Park and Capps example, Brian Brigham,'s master's thesis, of which I was the major professor, and the work by Alviola and Capps in 2010, where we discussed this issue. My argument is that the appropriate cutoff is not necessarily 0.5, but the number of observations which conform to the situation that y equals 1, the first alternative, divided by the total number of observations. So there's a picture of me with my cutoff. And what is actually generated then is an expectation prediction table, or prediction success table. So you'll notice here we know if you'll consider the actual columns, we know the number of times that we actually observe 0, the number of times we see a 1. But on the predicted side of things, remember, we'll predict a 0 if the predicted probability is less than the cutoff, and we'll predict a 1, the first alternative, if the predicted probability is greater than that cutoff. And once we have this mechanism, you'll see on slide 20, the circled entities A and D. These are the correct predictions. So that sum divided by the total number of observations, if we do this either within sample or a training sample, gives us the percentage of right predictions. But we can also determine how well the model does in correctly predicting the first alternative or the second alternative as well. In the case of predicting the first alternative, or when y equals 1, what we would take a look at here based on this 2x2 prediction success table is the ratio of D divided by B plus D, and that's called the sensitivity, and then correspondingly the fraction of the observations for which y equals 0 that are correctly predicted, which is known as the specificity, the ratio of A over A plus C. So it's important that we generate this output along with the estimated parameters, the goodness of fit, and then this prediction success table. So let's discuss all of this with the use of a sample problem, and I'm going to use probit to illustrate. This is an actual voting problem where we had a local election in Troy, Michigan, actually. The dependent variable is the probability that the 90 out of the 95 individuals who voted, that they voted yes. And there's a number of explanatory variables here called pub12, pub34, pub5, priv, yield, school, the log of income, and the log of PT con. So if we take a look at these variables, y equals 1 is when the individual votes yes, or 0 when they vote no. There's 95 individuals. Pub12 is a dummy variable, and it corresponds to the situation if 1 or 2 children attend public school within the voter's family. Pub34, another dummy variable if 3 or 4 children attend the public school within the individual voter's family. Pub5, if 5 or more children attend public school within the individual voter's family. Priv equals 1, another dummy variable if the family has 1 or more children attending private school. And if we stop right here, if we look at pub1, 2, 3, 4, or pub5, we would expect that coefficient to be positive, meaning if they're going to vote yes for a local public school bond issue, having children go to public school would, we would expect the likelihood of the individual voter voting yes to occur. However, if the family has children attending private school, we might hypothesize that coefficient being equal to a negative value. Other variables, school equals 1 if the individual voter is employed as a teacher, either in private or public school. We'd expect the coefficient there to be positive. The number of years the individual voter has lived in the community, here the argument for the sign of the coefficient may not be obvious, could be positive, could be negative. And then we have the natural log of household income or property taxes paid as also potential drivers. And note, you can use log transformations in the explanatory variables and the calculation of the marginal effects we'll discuss concerning these. Do we need to actually use logs? No, it's just part of the functional form that was used in this example. So, how do we actually handle this? Now, what I'm about to share with you is output that I use with SAS. However, there's nothing magical about SAS. EView, Stata, R will essentially do the same thing. But in the case of SAS, and this is on slide 24, we're using proqlim. So the way we use that, if for those that are SAS users, proqlim, and then you'll have your model specification, just as we've discussed. The key option to get a probit model is discrete paren d equals normal close paren. And then this output statement is also good because it creates an output data set called probit results, which has in it x beta, which is the z value, prob, which is the probability value, and marginal, which gives the marginal effects associated with each of the explanatory variables. Now, mils is not necessary with the use of probit or logit models, but it will play a role in centered response. So for the time being, we'll just let that go. There's also goodness of fit test that can be done, and the McFadden R squared will be what is printed out. And here are the procedures to retrieve all the marginal effects associated with this situation. So we were able to retrieve all of the information. On slide 26, what I've given is, and SAS is not very good at providing a cutoff. One has to program that cutoff in here. The cutoff is rather strange, 0.621056 on slide 26. But what that corresponds to is the number of observations of individual voters who voted yes divided by 95. It turned out to be a little bit more than 62% of the sample voting yes. Just to show as a comparison the conventional cutoff of 0.5. EViews, for example, you don't need this programming set of statements. It allows you to go ahead and specify the cutoff directly, and it will create that expectation prediction table. Now, as we go forward, I'm providing descriptive statistics now of this sample on slide 27. And the first thing I'm going to discuss here is the linear probability model. It's not good practice to do the linear probability model when you have the probit or logit capability at your fingertips, but nevertheless, I'll show you how to do that. Now, if you look at this, the R squared is 0.17, not a surprise, cross-sectional data. And collinearity is not an issue here, although one may have expected a collinear relationship between income and property taxes, that is LINC and LPTCON. But here are the parameter estimates. Now, interestingly enough, with OLS, the parameter estimates are the marginal effects themselves, meaning, for example, in the case of pub 1, 2, 3, 4, and pub 5, the reference category or base category is no children attending public school. So in the case of pub 1, 2, 3, 4, and pub 5, all the estimated coefficients are positive as we hypothesized, and the correct interpretation is the probability is higher by 0.10668 if the individual voter has 1 or 2 children attending public school relative to the case of no children attending public school. The PRIV estimated coefficient is negative as we hypothesized. Whether or not the individual voter is a school teacher, high probability or the probability is going to be higher by 0.313 if the individual voter is a teacher relative to a voter not being a teacher. And if you'll note, higher income households are more likely to vote yes, but those households that pay higher property taxes are less likely to vote yes. Now, what are the key factors based on the p-values? Well, based on the p-values, it looks like um, income and property taxes are drivers, along with whether or not the individual voter is a teacher. All of this on slide 29. Here is the familiar collinearity diagnostics that justifies the fact that there is no collinearity. And with cross-sectional data, even though we didn't really need to do this, we also have no evidence of autocorrelation. Now on slide 32, we see at the bottom here, value is the value of the dependent variable, 0 or 1. So we have 36 individuals who voted no and 59 individuals who voted yes. And now we're going to begin the estimation of the model, the probit model, with the use of maximum likelihood, and the quasi-Newton procedure is used. Note that proc-QLim also gives the familiar AIC and Schwarz criterion, just in case there are alternative versions of the model that one may want to employ to figure out which model gives the better or best indication of model performance. And we can do this for the probit model, we can do it for the logit model, and although they're very, very similar, we can actually, on the basis of model selection criteria, make a determination if the probit model is better than the logit model. And here is the list of the goodness of fit measures that I discussed, and the one I've highlighted here on slide 34 is the McFadden LRI likelihood ratio index. And if you look down the page, all the way from the Aldrich, Nelson criteria, the various Craig-Euler criterias, the various Strella criterias, the highest R squared is McKelvey-Zavonia, but really the most popular and the one that's often reported is the McFadden's likelihood ratio index. And with the QLim procedure, and this is on slide 35, you'll see the estimated coefficients, but these are no longer the marginal effects. You'll see, based on the last column, which of the drivers are most important in affecting the decision to vote yes in the school bond election. And they, similar to the linear probability model, are school, the log of income, and the log of property taxes. If we move forward here, on slide 36, we see the likelihood ratio, which is the analogous to the overall F statistic that we use in conventional regression analysis. And with this low probability of 0.0112, it indicates that at least one of the coefficients is statistically different from 0, and we already have talked about which of those parameter estimates fell into that category. We can also do a bunch of tests on subsets of coefficients. On slide 37, you'll see coefficients corresponding to children in public school and whether or not one or more children attends private school. And notice the p-value of the likelihood ratio test here, which is a chi-squared test with 4 degrees of freedom, being 0.5413. That indicates whether or not the family has children attending either public or private school. Makes no difference really in the outcome of voting yes in the election. Now, as I mentioned, once the parameter estimates are obtained, then you can get z-values. So for example, how do we get the z-value for the first observation? And that z-value is 1.68132. And you'll see, and you don't have to do this because this is what proc-QLim does, it will write out, or if we had to derive it, we'd use the estimated coefficients, and then we put in for the explanatory variables here, their actual values, and with this linear combination we get Z1, which is 1.68132. That, with that value, based on the integral that we discussed associated with the cumulative distribution function, which is a normal distribution, associated with the probit analysis, we get a probability of 0.95365. That is our prediction that this first voter will vote yes. And in fact, if you'll see, that voter actually did yes. And the second observation, the probability that's generated is 0.32326. And with that probability, we would argue that that would likely be the case, that the voter would vote no, and in fact that was the case. So we get the set of probabilities here in the fourth column. We compare those to the actual values, and that will ultimately set the stage for our prediction success table that I'll discuss subsequently. So we do this for each of the observations. Now, the next thing that we would be interested in getting are the marginal effects. And on slide 40, you'll see that I've written out the marginal effects, which is the estimated coefficient times the probability density function, little f of z. Now remember, you'll have to recall the probability density function, which is equal to 1 over the square root of 2 pi e to the minus z squared over 2. That's indicated on slide 39. But again, proculim will automatically compute these marginal effects as indicated by, on slide 40, MEFF underscore P2 underscore P1 PUB12, and then correspondingly for pub34, pub5. This information comes from the use of that output statement in SAS. Depending on the package, they may or may not present the marginal effects, so it's important for you to understand where these marginal effects actually come from. So we do this for all marginal effects here. Now when we get to, on slide 42, when we have log transformations, for example, income or property taxes, PTCON, remember on slide 42, the correct marginal effects are given as little f of z times beta. But in the case of log transformations, the use of log for income, in order to get that correct marginal effect, it's not necessarily just equal to the estimated coefficient, but the estimated coefficient divided by income here. So technically, you need to scale each of the parameter estimates by dividing by income and PT-con because of the use of the log transformations. This was actually not done correctly in SAS. So in order to take, on slide 43, the marginal effects for income and PT-con, because SAS was unaware that this variable was actually a log transformation, one would need to divide by a measure of income or PT-con in order to put that on the same level footing with all the other marginal effects. Now at the end of the day, on slide 44, we're going to compute each of these marginal effects for each observation, and then based on the means procedure, or you can use the median procedure, get a measure of the marginal effect. And this is all summarized here on slide 44, but one would have to scale the marginal effects for income and property taxes to get the correct marginal effects. And here on slide 45, one could use the median. Either way is acceptable as standard practice. Now, how do we get the prediction success table? Well, as you saw earlier, we get the predicted value, we know what the actual value is, and what we need to formulate that prediction success table is the cutoff value. Well, the cutoff value here on slide 46 is 0.6210526, the ratio of the number of observations corresponding to yes divided by 95. One could also use a cutoff value of 0.5, but you're going to get different values, and the reason I like the cutoff of 0.62, it reflects the characteristics of the sample that voted yes, as opposed to just a 50-50 proposition. And on slide 47, now we actually see the prediction success table with the cutoff value of 0.6210526. So you see the number of correct predictions is 28 and 34. That is, we predicted within sample here that 28 of the observations would vote no, and they actually did. And in the case of 34, we predicted based on that cutoff value, 34 individuals voted yes, and they actually did. So in total, we got 62 out of 95, or the percentage of correct predictions is 65.3. That is, within sample, roughly, we correctly predicted 2 out of 3 individuals making the correct decision. Now, if you'll note, based on sensitivity or specificity, for those that voted yes, we were able to get 34 out of 59, or our number of correct predictions is about 58%. And for those that voted no, we got 28 out of 36. So our model was especially good at identifying those individuals who voted no as opposed to those that voted yes. Now, in the next slide, how do you get the logit procedure? Well, again, with proculim, the setup is actually the same except for the option. The option is discrete D equals logistic as opposed to D equals normal. So in the remaining slides, we can actually go through the same thing. On slide 49, notice here's an AIC and SIC. So if you wanted to know if the logit or probit model was better, one could compare the AIC and Schwarz criterion. They're going to be very, very similar. And we get similar goodness of fit measures. And in fact, going forward, essentially everything here will be the same as we discussed previously. So go ahead and take a look on the subsequent slides going forward, slide 52, 53, 54, 55, 56, 57, 58, very, very similar. And then if you take a look at the prediction success table, we can actually put that together for the logit model, and the performance is the same as the probit model. Now, to summarize this, and this is the last slide on page 61, I want to point out several things, and then we can conclude our discussion on chapter 13 with the case of binary choice models. So in the sample problem, on the first column, we see the variable. The second column is the OLS parameter estimates, and in parentheses are the standard errors. And we, with an asterisk, indicate those variables that are statistically influential if we use a level of significance of 0.05. In the third column, under the heading probit analysis, we report the parameter estimate and the standard error. But these parameter estimates are not the marginal effects, whereas under the heading of the OLS analysis, the estimated coefficients are the marginal effects. So to get the marginal effects for the probit analysis, we need to multiply the parameter estimates times the probability density function. Now, unlike what I did earlier, just to give you an alternative as to how we could compute perhaps more easily the marginal effects, what I've done is to take each of the explanatory variables, and don't forget the intercept, and set them at the sample means. Then based on the sample means, take the product of the means of the variable times the respective parameter estimates and get that linear combination. So you see on that basis at the bottom of this table, at the sample mean zi equals 0.42109, that would be the z that we get with the probit. And consequently, based on the probability density function associated with the standard normal, that particular z variable gives rise to little f of z of 0.3651. So if we were to multiply each of the parameter estimates by 0.3651, we get the marginal effects, and they're indicated here. 0.1343 is the marginal effect for pub 1.2, 0.2523 for pub 3.4, and so on. And if you were to compare the marginal effects here with the probit with the OLS, which in fact are comparable, in many cases what that would have meant is that you would have used the wrong marginal effects if you had used the OLS analysis. Now in the last two columns, we didn't say much about the logit model in this particular example, but I've provided the parameter estimates. But the first thing to notice, if one were to compare the parameter estimates from the logit model with the parameter estimates from the probit model, it is necessarily true that each of the parameter estimates for the logit are bigger, larger than the probit model. That is absolutely a must. And if you were to multiply the parameter estimates times 1.6, essentially, you would be able to go from the probit model to the logit parameter estimates. The rationale for that is based on the similar distributions between the probit and logit model. This was a finding that I had made in 1983. That's almost 30 years ago, only to find out that others had made the same discovery, although I made it independently. So one doesn't compare the parameter estimates between probit and logit because it's guaranteed that the logit parameter estimates are higher by a factor of 1.6. But going through the same process, you can compare the marginal effects between probit and logit, and once again you have to get the appropriate z value, and at the bottom of the table at the sample means the appropriate z value for the logit model is 0.69698. The corresponding value of the probability density function is 0.2219. You may want to verify why when you get a value of z of 0.4210 for the using probit, consequently you get the probability density function of 0.3651, and the same for the logit model. When you get an index of 0.69698, how do you get the underlying density function of 0.2219? Likely I'll ask you to do that on one of your homeworks. For the final problem set. Now, when you do that, you can't compare the marginal effects for probit and logit, and the thing to notice is that the marginal effects are very, very similar. So in the case of a binary choice model, and again, I made this discovery in a paper in the American Journal of Ag Economics in 1983, although from time to time you could get similar answers, generally probit or logit, pick one, they're going to give very, very similar answers. But do not use the OLS estimates because they, even though they provide consistent and unbiased parameter estimates, they are not the best to use in the case of binary choice models, predominantly because they could generate predicted values that are bigger than 1 or negative, and of course we don't want that because the predicted values are probabilities, and probabilities cannot be negative or 0. Thank you very much for listening to this lecture. I miss you all. I'm sure if you have questions you can always email me, and you'll get an opportunity to work on problems like these with the use of probit and logit models on problem set number 4. Thank you so much.